Okay, so like I was explaining, one thing that should not confuse you here is that however way you define a cathode under galvanic cell is the same way you're going to define the cathode here in terms of reactions. Now, every time where reduction happens in an under electrolysis, under electrochemistry, I mean, whichever end carries out reduction is the cathode, irrespective of the sign that it has. So here, just know that reduction is taking place on the negative end of the terminal, unlike in the galvanic cell where it takes place on the positive end, meaning oxidation is going to take place on the anode end, which is the positive end. So this is one thing where you don't need to get confused. So if they ask you, what's the similarity between the cathodes in an electrolytic cell and that of a galvanic cell? The similarity there is that in both, reduction takes place on the cathode. So whichever electrode is going to be the cathode will undergo reduction, irrespective of which cell you are looking at. Okay. So the inert electrons, ones that do not chemically react during electrolysis, the most common is graphite, which is copper, carbon, platinum, or gold. So these are the three that you're going to be looking at most of the times. These are the three options you have to choose from. You are drawing the cell for yourself, or you are asked the question where you have to come up with this. The electrodes, you don't need to tell us that this is net a cathode. No, you will give us one of these options as what is being used for you to have a full mark. Otherwise, just by saying inert, you'll be given half. So say PT for this one and PT for that one. So that's how it's done. So these are just actually explaining what I've already explained there. Okay. So in order for the current to flow, negative charges must move continuously from the negative to the positive of the generator, and at the instance in time, electrical neutrality must be maintained at all points in the cell, meaning the cell should be electrically neutral. This is why in a galvanic cell, you have the salt bridge to bring about cell neutrality. Okay, so electrical neutrality is when in a cell you have no net charge. Okay, inside the cell there is no net charge. That is cell neutrality. Therefore, electrons must be simultaneously transferred at the two electrodes. What happens at the negative electrode? Sodium ion approaches, the electrons must be transferred from the electrode to melt, complete the circuit. And okay, so this is just explaining what is happening when electrons arrive here. Electrons are picked up from this side, taken to this side. Now, when the electrons have arrived at this electrode, what is going to happen? What is going to happen is that this electrode should be maintained. The neutrality in here should be maintained. So if we allow electrons to start coming in on this side is going to become a bit more negative than it should, and therefore there will be no neutrality. So for there to be neutrality, the sodium ion begins to react with those electrons. Therefore, this is being reduced to sodium metal. And the bromine, this side, keeps losing electrons, so bromine is going to be changed into bromine atoms, so that the negative charge, the positive charge, the electrons around are maintained at a neutral electrical condition known as electrical neutrality. So what this here is just them explaining what is happening. This ion approaches the negative electrode. The negative electrode is rich with negatively charged electrons, so they begin to reduce this into a solid. That is that. So the reduction must take place at this electrode. Electrode is the cathode. So that is where reduction is taking place. Why is it called the cathode? It's because that's where reduction is taking place. Otherwise, we would have maintained anode and stuff, but because these are named not because of the signs that they have, but because of the processes that take place where they are. So a cathode electrode, all the time reduction. Anode electrode, all the time oxidation. Okay, so here again, they're just explaining what is happening to the bromine electrode there. So electrolysis of aqueous solution using inert electrodes. So we consider that the cell diagram has been given. A current is carried out in the circuit by the movement of electrons from. Okay, so I think this is just a repetition of what we've actually looked at. So the negative electrode, two possibilities for reactions. Okay, so the electrode reaction requiring less energy will occur. Sodium is less reactive metal. With that, therefore, this is difficult to reduce. It takes much less energy to reduce that in water than it does this. H2O is reduced to that. So here they're just trying to compare the reduction abilities, how easy it is to reduce this as compared to a given metal. So you will use the electrode potentials to answer your question. Look at the reduction potential of this one and look at the reduction potential of that one. Which one of the two has a higher reduction potential? So the same here, they're looking at the possibility of oxidation. So they've gone to the positive potential. I think that was a repetition of what we are from looking at. All right. So now every time you calculate in this particular question, your answer is going to come out negative for the cell potential. Why? These cells are not spontaneous cells. Okay. And then we look at overvoltage. So overvoltage, in theory, one should be able to use the next equation to predict what electrode reactions will occur. According to the next equation, the reduction potentials are this as a function of that is. So when you do this computation at pH is equals to 7, E is equals to negative 0.414 volts. This already tells you that the reaction is not spontaneous. Therefore, only metals whose reduction potentials are less than this can actually react in here. Okay, so this is basically just them having a lot of things to say or talk about, or when notes have been made, we are just making a point. This is an emphasis on the already outlined point here. So this is an emphasis, and these are examples of where this is being used. So you have zinc and you have chromate there. So now you compare which of these is going to have a spontaneous reaction and a non-spontaneous. So if you check negative 74, and if you check negative 76, these are the two metals that you have, and this is the potential for water. So they are saying, therefore, only metals whose reduction potentials are less than the reduction potential, this one, are the ones that will plate out, okay, should be reduced and plate out at the cathode in the electrolysis of aqueous solutions of electrolyte. So that is what it is. So this means that it should not be possible to reduce zinc, whose potential is that, and chromate, whose potential is that, and iron, whose potential is this from the aqueous solutions. In fact, these metals do plate out of solution in electrolysis. Okay, so it is going to be difficult if you check 0. When you are looking at the cell potentials, you follow the negative. So this and that, this and that. So you check how are the potentials. If their potentials are smaller than this, they won't play it out. If their potentials are larger than this, they will play it out. So the problem is that the next equation is a thermodynamic equation that says nothing about kinetics. So some reactions such as that are too slow to occur at the. So what this is just telling us is that we can calculate. We carry out a calculation, and we find the cell potential overall. This tells us that the way we are going to write our equation can be, the reaction will be spontaneous. But what it doesn't tell us is that how long will the reaction take before it takes place? Okay? There will be reactions where you calculate your potential. It comes out positive. And yet, that particular reaction will take years if you just leave them like that for it to happen. So for that particular reaction to, this is what they are saying here. That's just, the next equation just tells us that this reaction is going to happen, but it does not answer the question, how will it happen? When will it happen? How fast will it happen? So those are the restrictions that come with the next equation. That's why for you now to answer these questions, you will need the knowledge of kinetics, where we start now looking at the rates of reactions, how fast the reaction is happening, what is the rate determining step in the reaction, and all that. So this is what the next equation's limitations actually are. And then over voltage is actually the potential at which an electrode reaction takes place. The potential calculated from the next equation, okay? So over voltage is the potential at which an electrode reaction takes place. You calculate using the next equation, you find what this is, that particular value, that potential that you find, that voltage you get is the over voltage. And the over voltage depends on the electrode reaction. So the current passing through the cell and the electrode material, hydrogen overvolt is an excess of 1 volt, or not uncommon. So hydrogen will only be reduced when, or oxidized when, there is an excess of 1 volt. So when 1 volt is applied, then that is reduced. So you want to find what potential is required to reduce a certain, or to oxidize a certain element. When you calculate that particular value, that value that you get is the over voltage, because the reaction at that, immediately you go above that particular value, it begins to react. The reactions begin to take place. Okay. Rules for predicting aqueous electrolysis, 1930. The moment you, when you are predicting the reactions, always know this. I've already told you this. This is what I'm saying. These are just emphasis of the same point. What is going to happen here is that when you are looking at the cathode, it is an electrolysis cell, cathode reduction, anode oxidation, irrespective of what they give you, just get the equations and write them as they should be. Cathode oxidation, cathode reduction, anode oxidation, and everything else follows through. So by giving examples here, inert, and then cathode, anode. This is the solutions that you have. Nickel iodate, potassium carbonate, calcium nitrite, and copper sulfate. So there are half reactions. You're right. This is the half reaction, and stuff. So remember, anode reaction is oxidation reaction. So this has to be oxidized, that has to be reduced all the time, all the time. Anode oxidation, cathode reduction. So there's really nothing difficulty about you coming up with the equations that are there. And it is out of these that we start doing electroplating of stuff and other things. So I think today it's already 18:30. We will end here. Tomorrow, when we meet, we finish up and we start looking at questions under electrochemistry. So in the last two sessions that we should have, we will finish this particular part. Meaning next week, Monday, I will give you a check-up test. Okay? Next week, Monday, you have a check-up test just to see how much information you've grasped from the topics we've done, because so far we've done quite a number of topics, if not 4 now, then 5. It's not right for us to just continue going and going and going without actually assessing how much you've understood what we've done. So at the end of this week, we should be done this part, and we will have a quiz, not a quiz, a test actually, next week, Monday.
Sir,
Yes.
I was kindly asking if you could send those notes to the group.
Okay, let me do that.
All right, thank you so much.